about, and we're going to sort of talk about how we might use some of these machine learning methods to understand some of the systems, particularly this is now going to switch from hearts to brains in sort of brain imaging topics, and then we're going to use, I'm going to talk about very simplistic sparse Bayesian learning methods, and then Yu's going to take off and show how some of the research she's been doing on a purely machine learning basis might sort of enhance some of the things that we want to know, and sort of why using cutting edge tools from machine learning may well be the way to go in some of these applications. So we've heard a lot about positron emission tomography, but I'm going to give a sort of very brief overview of what it actually sort of does from a sort of machine level system. Basically, we have a compound, as we saw. FDG was a nice example that we had in the previous two talks, where you radio label glucose effectively with some kind of positron emitting radio label. Now, in actual fact, I'm going to use some different tracers in this talk. I'm going to be talking about something which looks at the opioid receptor system in the brain, so pain effectively, and then something else that looks at the sort of reward system, which is often linked to addiction. I'm going to look at two different tracers there. FDG is typically labeled with fluorine-18, which has got a sort of long half-life of about 2 hours. We're going to be talking about some compounds that are typically labeled with carbon-11, which has a half-life of about 20 minutes. And basically this compound gets radio labeled, the person goes into the scanner, the radio label decays and produces a positron. The positron meets an electron, matter meets antimatter, you get an annihilation, and that produces energy in the form of two gamma rays, which come out at about 180 degrees from each other, not exactly, but almost, and they are detected in the rings of the scanner, and you can use these line integrals to reconstruct images that look like this, which tell you where the particular concentration of the radio-labeled compound was. So that's exactly what happens in the FDG example in the heart. You look to see where the build-up of FDG is. The nice thing about FDG is it kind of sticks around, and so you can just take one shot. Inject the patient with FDG, leave them for a couple of hours, come back, image them, and then you look to see where the FDG is accumulated, and that gives you a pretty good idea of where the FDG lies. For the kind of compounds that I'm going to talk about, is in actual fact the whole time course is going to be important, because you're only looking at 20-minute, something with only a half-life of 20 minutes, and it's going to have a rapidly changing underlying biological system involved, and so you want to try and understand the underlying biology as well as look at particular instances over time. So that's the sort of underlying mechanism of the sort of data that we want to look at. What's the kind of actual data that we get out of the system? Well, we saw the sort of individual images of the heart with FDG. Here's the brain with a compound called sharing, which looks at the dopamine system. You get a three-dimensional image, so you get sort of maybe about 1 million voxels in space, and then associated with each spatial location is a time course. Now, these are not linear time courses because these are chemical reactions effectively. There's an input into the system, and then slowly in this case, the sharing compound undergoes various different chemical reactions. It may be binds to the dopamine receptors in the brain, binds on and then comes off. It may pass into the blood, across from the blood into the brain and back out again. And these various different underlying chemical reactions dictate the shape of this underlying curve in time. And there's one of these curves at every single individual voxel in the brain. And so what we'd like to be able to do is be able to analyze the time course nature across all of space in order to really understand what the dynamics of the system are, and from that to understand what's going on with various different brain regions. Are there areas of high uptake, which possibly mean that there's large amounts of dopamine binding going on? Are there areas that are low uptake, which basically means that the tracer is washing in and out of the brain? And we can do that much better if we consider the entire time course of the system rather than a single individual snapshot, because these things are quite noisy and they're also sort of decaying very rapidly. And as you see, it takes a while for the data to actually get to the peak position. So this is the kind of pictures we had there. As you saw here, you get some nice smooth curves. Well, this is actually data that's been smoothed around to make it look kind of nice to understand what's going on. The real data actually looks really noisy. So these are the kind of curves you get from sort of 5 random locations that have sort of got something going on in them. you'll see that it's very noisy, so there's a lot of statistical noise in it. This noise is not sort of is not homogeneous, it's quite heterogeneous. You see that where there's high amounts of signal, there's quite a high lots of noise. Where there's sort of low amounts of signal, there seems to be lower amounts of noise. Well, that's not surprising. We're talking about radiation here. This is sort of Poisson decay. We expect that sort of the amount of variability to be proportional to the amount of signal that we see. So we have these sort of curves that are like this, which have got a noisiness, but we have to take this into account into our analysis. When we look at our analysis, we want to understand how we take into account that the middle portion of the signal is more noisy than the end portion of the signal, for example. So the way we want to do this is by building models that underlie the system, and in actual fact there's quite a lot known about the biology of these systems. You know, we know that this is some kind of chemical reaction, that the tracer is binding onto systems and coming off. It's going from, so this is the blood that's delivering the tracer to the brain, and then it crosses into the brain, which is this nice box here, and this is one particular voxel in the brain, and it then binds on and off. So maybe it binds, it comes into the brain into this sort of free compartment, then maybe it binds to the dopamine receptor in the case of the dopamine tracer, or maybe it binds to another receptor that's not dopamine, and so it's non-specifically bound to the dopamine receptor. Maybe there are lots of other different reactions going on. What we typically want to do with the kind of models that we generate is figure out a few things. First of all, we want to understand what these kind of rates of reaction are, because that's going to tell us something about the system. But we'd also like to know the number of compartments, the number of compartments that are occurring in this system, and use that to understand somewhat about what the data can actually tell us about the system, because the data is very noisy, and even if we believe this is a very, very, very complicated system, the data is not going to support estimating that system. So we want to sort of somehow, from the data, learn what the system, what we can estimate about the system. So in equation terms, effectively what we're doing is we're convolving the input into the system. This is the blood input into the system, which we get to measure. In many of these scans, you have a online blood sampling at the same time, which records the amount of radiation that's coming actually into the blood, so it goes into the system. Although in some of the later slides I'll show some pictures where this has been generated by using an area that's known to be devoid from anatomical and post-mortem studies, known to be devoid of dopamine receptors. You can use that as an input into the system itself, because you know it's not being contaminated by the underlying dopamine receptors that you're interested in. You can use that as your input into the system, and then this part comes from the reactions between moving from this compartment to this compartment, or this compartment to this compartment, and what we're interested in is the rates that these reactions occur, and then the number of compartments that we have in our system that are at least identifiable from our techniques. So typically, though, we can't really get good estimates of individual parameters. We can't say, well, it's transferring from blood to brain with this particular rate constant. We can't say it's binding specifically to a particular area or specific receptor with this particular rate constant. But what we can do is get some kind of function of all the rate constants together, which is usually known as the volume of distribution. And effectively, it's just a ratio of the rates constants themselves, and it kind of defines what would happen if you, instead of inputting the system with the input that comes from giving the injection of the tracer and then slowly washing into the system, what would happen if you could give a bolus single input into the system, and what would be the resulting result if you allowed that recorded then the amount of radiation, the amount of binding that would happen over as long as you want to measure, in fact, over infinite amounts of time. And you can actually solve this because it's a nice exponential system. It has a nice closed form solution in terms of the underlying parameters that you estimate, and it tends to be this ratio, this volume of distribution VT, that is the biological element of interest that allows clinicians to understand when there's differences between subjects. So often this is in the case of sort of patients, maybe it's schizophrenic populations or epilepsy populations. You're interested in how the binding of this, for example, in the epilepsy group, the data you'll see later as part of a study on the opioid receptor system. Do opioid receptor systems differ between epilepsy patients and normal controls? And so the way they measure the difference is through this parameter VT, which sort of measures the sort of total amount of change in the system between the two population groups. So from a mathematical and statistical point of view, we want to be able to solve those equations. We want to understand what the underlying systems are and work out a way to solve them. But unfortunately, these systems tend to be very, very large systems to solve. So we can linearize the system. We can turn this equation into a linear system by taking a set of basis functions for this, by taking a range of values for this and setting up a basis function, and then our input data, which is the PET signal data that we see, is some linear combination of some parameters here and some basis system here. And that turns into this equation here. We're trying to minimize the distance from our data to our basis system and the weights on that basis system. And it turns out we know quite a lot about this because it's a chemical reaction and because we have put parameters that are sort of weights going from this compartment to this compartment, and then also weights that come from this compartment back to this compartment. We know they have to be positive, otherwise we just flip the signs of our arrows. So this arrow would point this way and this arrow would point that way, and that would make the system unidentifiable. So in order to do that, we have to say that the values associated with this arrow are positive, which is exactly what this says. It says that the weights that we estimate must be positive, and that's one way of solving this system, and it's a well-known, it goes back to the 1990s, of way of solving this system. Now, any statistician in the room will immediately recognize this as the lasso penalty. This is a very sort of very famous something that's come out of statistics in the last sort of 20 years. There's huge amounts of statistical literature on this. It basically weights says I want to put a weight, and the more basis elements I add in, the more weights I have that are present, then the more penalty I pay for doing that. And you can solve this, and this also gives you a solution to the problem. This is called basis pursuits. It's called depicts in the PET literature, and basically allows you to solve, again, this over-complete system where you have very, very few observations. So maybe you'll have sort of up to 30 to 40 time points in your PET time course, yet here you're trying to solve it with a basis function system where maybe you have 1,000 basis functions that you want to choose from. But you believe there are only a very few, because you believe there are only a very few associated with each number of compartments. So each compartment you see corresponds to one basis function, and you basically only want to select a very few number of these weights, and this lasso penalty encourages sparsity. It tries to shrink down the number of weights to zero so that this penalty can be as small as possible. So they're the two sort of standard ways of doing this, but you can also take a machine learning approach. And a machine learning approach that was developed at the beginning of the 2000s was something called sparse Bayesian learning. And this takes the sort of opposite to the sort of frequentist approach that the previous two methods look at, and this takes a Bayesian approach to the problem. And it says, I have a linear equation, which is my data is corresponds to some basis function system and some weights, and I want to understand how to estimate that system. But I believe that these number of weights in my system is very small. And that's a prior belief. That puts me into sort of Bayesian statistical territory. And therefore what I want to do is I want to put priors on my data. So I'm going to have this as my new model where I've got some error on the measurements I see, and I'm going to put some prior distribution on my weights, and that's going to allow me to encode that I believe that the system is rather sparse. And then I want to learn the system under the assumption that there's actually only a few vectors in my basis that actually are useful in the system. So we can define hyperparameters and hyperpriors on our data in order to be able to calculate this. So we define a very large number of hyperparameters that control each of our weights. So for every weight we define a hyperparameter, and that hyperparameter just controls the variance. And as this hyperparameter gets bigger and bigger and bigger, this inverse gets smaller and smaller and smaller, and this probability the weight is anything other than zero tends to zero. So it basically fixes as the alpha I get bigger, as these alpha I tend to infinity, the probability that the weight is anything other than zero is zero, so the weight is zero. And similarly, we put a hyperprior on the noise, and we can estimate then the noise in the system as well, and we can play these things off. So we're interested in how we trade our alpha I, the priors, on our penalty, on our weights, and our noise in the system, and use that to try and estimate the underlying amount of noise and number of weights in the system. And we use an uninformative prior initially and say any weight could be part of the system, any amount of noise could be in the system, and then we try and learn these parameters from the data. How do we do that? Well, we use something called type 2 maximum likelihood, which basically is an iterative approach. We set up, and the fact that we've set this all up as nice Gaussian data means there's a lot of closed form solutions to this, and we can work out the probability of the weights dependent on our particular priors that we have, our hyperparameters on our weights, and it turns out to be a nice closed form normal distribution determined by the hyperparameters, and then we iterate. So we look at, for a given set of hyperparameters, what is the best value of those hyperparameters, or for a given set of hyperparameters, what's our mean and variance, for then a given set of mean and variance, what's the best value of our hyperparameters, and we iterate backwards and forwards until we get a iterative re-estimation that tends to fairly quickly converge. And then that gives us a probability of our weights given our data, and many of these hyperparameters will tend to infinity, which means that many of the weights will drop out. In fact, almost all the weights will drop out. It's a very encourages huge amounts of sparsity in our system. So what do we kind of get out as our plots? Well, basis pursuit is the L1 normal minimization. And what we see is that we get slightly lower values. If you look at the color bar is the same. And if you look for the VD plot, this is of diprenorphine, which is the PET data generated that looks at the opioid receptor system. So this is the a particular patient with looking at their value of VD, the amount of receptor binding to the opioid system using this carbon 11 diprenorphine. And basically what we see is that there are slightly higher values generated by basis pursuit than there is by sparse Bayesian learning. And the reason for that is that basis pursuit is well known to have a bias associated with it, because you have this L1 penalty on it, and you can only have positive data because we know the positivity in our parameters. We had a slight bias in basis pursuit, which seems, well, it's lower value. You can't tell whether it's right or not. We're interested in, we'll look at that in a second. But it's encouraging that we get slightly different results from the sparse Bayesian learning than we do from basis pursuit. What's possibly more interesting, though, is what's the kind of model that's being chosen. And we see that basis pursuit, while it does encourage sparsity, we're talking about 4 components here, so a 4-component model coming out of our data. We see that basis pursuit and sparse Bayesian learning, there is definitely a difference in the complexity of the model being estimated. And I think if you talk to a biologist and said from 20 to 30 data points, can you really routinely recover a 4-compartment model from this kind of data with the noise levels in PET at a voxel-wise level, you'd probably say no. I think it's probably a little bit infeasible that there's truly a 4-compartment model that can be identified from this data, whereas sparse Bayesian learning is typically picking a 1 to 2 compartment model for the data. What happens if we take a data set where we actually have a pretty good idea of what the actual underlying biology is? This is raclopride, which is again a dopamine receptor binding tracer, and we know that for raclopride, the cerebellum is a very good reference region, gives a very good input to the system, and in actual fact, a simplified reference tissue model, so a reference tissue model with 1 compartment in it, fits the data very well, and that's been biologically validated both in animal models and then in human models as well. And we've seen that this fits very well, and if you look at sparse Bayesian learning, you recover the reference tissue model, you get the same results with sparse Bayesian learning. There are basically no differences in this, whereas here with sparse Bayesian learning, of course, we've not assumed the model. We've let the data discover the model, whereas here this is the model that's been fixed, and you fitted the data directly to that individual model. So this is using sparse Bayesian learning techniques that are 20 years old. This is a sort of very simplified way of looking at sort of machine learning in this context. But of course, there's been lots of work on how you can take much more complicated and build in many more assumptions and many more interesting features that might occur in the data into sparse Bayesian learning. So while we've applied sparse Bayesian learning to the analysis of dynamic PET, we think it has particularly good properties. It has some nice theoretical properties compared to, say, non-negative least squares. We can actually look at the distributions of the noise underneath it. We can actually build models that contain uncertainty as well. And it seems to estimate values pretty well. It seems to have less bias. It does well when you've got the true model. It seems to recover the true model. At the moment, it's running somewhat slower than these. These are very fast to implement. This is a slightly slower implementation. We'd quite like to develop it to get it to run at sort of similar speeds. But this is very simple use of machine learning, sparse Bayesian learning techniques. And Yu's now going to talk about a much more complex situations where you can really build into further prior knowledge into the system. So.